Okay, we've been talking about solutions, I think, and remember, as we talked about, solutions are really those things that get the aqueous symbol next to them. They are a homogeneous mixture, which means everything mixes together and looks the same throughout. A solution, again, is made up of two parts: the solute, which is the smaller part of the solution, and the solvent, which is the larger part of the solution. So as we talked about, I think last time, you take something like water and some sodium chloride, and that salt is going to dissolve in the water, and that will make a sodium chloride solution, where the sodium chloride is the solute, and the solvent in this case is water. As we talked about last time, pretty much the name of a solution is pretty much the solute. And as we also talked about, the idea of solubility and kind of like dissolves like. And this is why something like sodium chloride is soluble in water. Water being polar has a positive and negative side, works really well with ions, which are positive and negative, and it's really opposites attract. So things, as we talked about last time, that basically have similar sort of interactions that they do with themselves, and they can do it with other molecules, make things soluble in each other. So things that are ionic and polar are soluble in each other. Things that are polar and polar are soluble in each other. Things that are nonpolar and nonpolar are soluble in each other. It's really you run into a little trouble again if you sort of want to cross over when you take something that's polar and nonpolar. Again, as we talked about, things that are nonpolar are essentially using pretty weak forces to hold themselves together. And something like water, for example, which is polar, wants to use something that's hydrogen bonding, which is a really strong sort of force. And these are different types of forces, which means when they go to interact with one another, they have a really hard time to maintain an interaction. And again, basically what will happen is they will kind of separate out. They typically will not mix. We also talked about solubility rules. And there are certain solubility rules that we could use to predict when we put together, for example, a couple of ions to make an ionic compound. Would we expect it to be soluble or insoluble? And remember that if something is soluble based on the solubility rules, those guys get the aqueous sort of symbol. If something is insoluble based on those solubility rules, then that is the guys that will get this solid sort of symbol next to it. So for example, things like group one, nitrates, acetates, they're soluble pretty much in everything. There's no exceptions, which means as soon as you see one of those guys in a particular formula, you know it's going to be soluble. It's going to be a solution. You wouldn't expect any type of solid to form. For example, things like chloride, bromide, and iodide, they are soluble in everything, but there are some exceptions, and there are a few exceptions, which are silver, lead, and mercury 1, actually. And what that means is if you have chloride, bromide, or iodine, and they're not with one of those three, then it would be soluble. But if it is with one of those threes, then it will become insoluble, and you would expect a solid to form, like something like silver chloride. We also talked about saturated solution, unsaturated solution. Again, a saturated solution is one where you pretty much have dissolved all of the solid that you could get in there at a given temperature. Unsaturated solution, you pretty much haven't hit that point yet, so you can continue to dissolve the solute until you hit a saturated solution. I think we finished up talking about electrolytes. And electrolytes are things that basically produce ions in solution. So they break apart and produce ions in solution, and that helps conduct electricity, which are light bulb example. Remember that there is a strong electrolyte, and a strong electrolyte 100% breaks apart into ions. Like sodium chloride solution. When you have a sodium chloride solution, you basically have sodium ions floating around. You got chloride ions floating around. You have none of these guys still together. 100% is pretty much just all those ions floating around. Because it produces a lot of ions really quickly in solution, it conducts electricity really, really well because of the presence of those ions. There's also weak electrolytes, which mainly stay together, but do break apart a little bit. So like HF, which is hydrofluoric acid, is an example of that. In solution, you will have a little bit of these ions here, but mainly this guy will still stay together. So because it's able to break apart into a few ions at least, it is considered an electrolyte, and it's a weak electrolyte. It also will be able to conduct electricity because there's a few ions floating around in that solution, but it will not be able to conduct electricity anywhere near what a strong electrolyte will be able to do. So again, our light bulb example, that was kind of a dim light bulb. You also can recognize that in equation form is it usually has these arrows that head in both directions, which indicates it's a reversible reaction. Forward direction going from reactants to products, a reverse direction going from products to reactants. So a weak electrolyte will have those arrows. A strong electrolyte is like a one-way arrow. Basically, everybody's dumping out there to the product side. Nobody's coming back the other way. But in a weak electrolyte, you got things going in both directions. There's also non-electrolytes as well, which are compounds that will dissolve in water like sugar. But again, there are no ions that are formed. And because there's no ions that are formed, then it will not conduct electricity. Any questions on any of that stuff there? I think we covered last time. Okay, so what we're gonna do is we're gonna go ahead in the notes, and then we're gonna go back in the notes. We're gonna skip ahead a little bit in our chapter 9 notes to here, and then, like I said, we'll go back afterwards in just a second as soon as we finish these. So we're going to talk now a little bit about some properties of solutions and some properties of solutions. For example, a semi-permeable membrane is a membrane that basically allows solvent molecules such as water and very small solute molecules to pass through, but it's not large enough, but not large solute molecules to pass through. So a membrane like this, although you can't necessarily always see it, there are sort of there's actually holes, if you will, in it, and passageways that allows certain size molecules to be able to basically pass through. It obviously prevents much larger molecules from trying to get through there. It's going to have a little trouble getting through that hole. So these type of membranes are used like a dialysis bag and stuff like that, where there's these little sort of holes, allow certain size things to sort of pass through, just like in your body, your membranes and your cells have cell membranes, allow certain things to sort of pass back and forth through based on size. Now, when we talk about colloids, colloids are much larger than solute particles in solution. They are large molecules like proteins, groups of molecules or ions that are together. They are a homogeneous mixture, and homogeneous means it basically looks the same throughout. So a colloid should look the same throughout. They do not separate or settle out. Colloids are small enough to pass through filters like filter paper. So if you have a funnel and some filter paper on there, they're able to basically come on through your funnel. But they are too large to sort of pass through the semi-permeable membrane, so they get a little caught there. Now, suspensions, on the other hand, are heterogeneous, non-uniform mixtures that are very different than solutions or colloids. They're often big enough to see with your naked eye. Like, for example, you threw some sand in some water or something like that. You will see the sand. Definitely, it's a suspension that's in there. I want to say charcoal, but I think maybe you guys use sand in lab. I don't remember what you guys use, but the suspension is, again, something that you really can't see. They are really big, which means that they do get trapped by both filters and also membranes. So if you go to filter something out and there's something in that sort of mixture and it gets trapped on the filter paper there, then it's going to probably be a suspension. Like I said, if you took some sand and water and you went to go pour it through a filter, the water will go through no problem, but the sand is obviously going to get caught up there on the filter paper, and that would be the suspension. Questions on that there. So here's our examples. We have our solution that are circles, our colloids, which are triangles, and our suspension, which are these red guys here. And you can see that the suspensions do settle out right at the bottom. Also, like I said, I guess kind of like oil and vinegar salad dressing, right? You can see all that stuff on the bottom, right? That's why we kind of shake it up right before we use it. That's sort of like a suspension. Here we have our solution colloids moving around in solution. If we go to filter all three of those things, you can see that both the colloid and the solution is small enough to go through filter paper. But once again, our suspension is going to get caught up there on the piece of filter paper and won't be able to go through because of its size. If you throw like a membrane here, which I think might be the lab days, is the state of the lab where you put everything in the dialysis bag and wait, and then wait, and then wait, and pop the bag at some point towards the end of the experiment. So here we can see in terms of our membrane, we have our solution molecules, which are small enough to get out. But again, a colloid and a suspension are too large. So it's kind of like a size filtering system. Your semi-permeable membrane won't be able to float out of the bag. Speaking of kind of how things move, let's talk a little bit about osmosis. Osmosis, the solvent water molecules moves through a membrane from a solution of lower concentration to a solution of higher concentration. So for example, if you had a little tube like so, and you had a membrane right about there, and on one side you had salt water, and on the other side you had pure water. So what happens is through the process of osmosis, the pure water is going to decide, oh, well, this side on the right here is more concentrated. More concentrated means it has more stuff floating around in it, basically. So the more stuff you have in a solution or something like that, the more concentrated it is. So what's going to happen by osmosis is water molecules will go through the membrane to the side that is more concentrated in an effort basically to like dilute it down to make it less concentrated. So we always kind of go from a lower concentration to a higher concentration. This flow of water molecules will kind of continue until it hits what is referred to as the osmotic pressure. And the osmotic pressure is a pressure that basically prevents more of that solvent water molecules from flowing from the lower concentrated side to the other side. Is basically equal to atmospheric pressure that's kind of pushing back down on it. So it'll stop that flow of molecules. The osmotic pressure of a solution depends on the number of solute particles dissolved in it. The greater the number of particles that are in there, the greater the osmotic pressure something has. Pure water has no osmotic pressure because pure water has nothing dissolved in it. There's nothing, particles or ions moving around. So you can actually measure, for example, the osmotic pressure. You could calculate it. By the way, in case you're curious, you can calculate the osmotic pressure. It is actually the ideal gas law. You could actually use that to calculate it, and it's really the same formula. But another sort of way to sometimes osmotic pressure is measured is in what's known as osmolarity, and sometimes abbreviated osmol, and that stands for osmolarity. And as we'll talk about here in just a second, molarity is one of the most common units of solutions in terms of their concentration. So for example, if I had two solutions, and we'll just say it was 2.5 molar sodium chloride solution, and the big M stands for molarity. And I had a 2.5 molar calcium chloride solution in this particular case. The way that we could calculate the osmolarity, for example, the osmolarity is equal to I times the molarity. I is what is known as the von Hoff factor. It essentially is the number of particles in a solution. So for example, if we look at both of these solutions, they both basically have the same concentration. They're both basically 2.5 molar, the exact same sort of concentration. But there is a difference at what happens when both of those guys go for a swim. So for example, when I take something like sodium chloride for a swim, that sodium chloride is going to break apart into a sodium ion and a chloride ion, which means in this solution, you basically got, if we just take one at a time here, basically two of these ions per sodium chloride unit that you throw in there. So for every one of those sodium chloride units, you get basically two ions. That means in this case, I would equal 2. It is as simple as that. There's basically 2 ions per unit, and I in this case would equal 2, which means when we go to solve for the osmolarity in this case, we would take 2, which is our I value, times the molarity, which is 2.5, and that's going to give us 5.0 osmolarity as sort of this osmotic pressure unit. Any questions on that there? Now, what happens with our calcium chloride example when I throw my calcium chloride in there? My calcium chloride is going to break apart into a calcium ion and 2 chloride ions, right? That's basically what CaCl2 means. That means basically every calcium chloride unit I throw in there for a swim, I'm going to get how many particles floating around? Going to get 3 particles, right? 1, 2, and 3 particles, which means in the case of calcium chloride, I would equal 3, which means if we do the osmolarity for this guy, it would be 3 times 2.5, which is going to get us, we got there 7.5 osmolarity. Now, when we compare the osmolarity, even though they both have the exact same concentration, which one has the higher, basically, osmotic pressure? It should be the one on the right, right? And it's because it has more particles floating around. So the number of particles that you have floating around has a direct effect on the osmotic pressure. Basically, more particles floating around, the greater the osmotic pressure. So even though, again, these two basically have the exact same concentration, because one will produce more particles, it actually creates more osmotic pressure than the other solution. Any questions on that there? So osmosis, once again, is that flow of solvent molecules from a lower concentration to a higher concentration. And that also is what happens, for example, when we do something like reverse osmosis. So what is reverse osmosis? Reverse osmosis is you decide to apply a pressure that is greater than the osmotic pressure heading the other way. And what that's going to do basically is force all of the water molecules back through the other way and push everybody back the other way. And if you have a nice filter right there, it's going to catch all the stuff you don't want, right? Kind of purify it that way, right? So what will come through the other side, you'll get back like your pure water. The filter will grab all the other stuff you don't want to come through. So reverse osmosis is this process where you apply a pressure greater than the osmotic pressure, pushes basically the solvent molecules back, like the water molecules, back the other way. Like I said, if you have a nice filter there, you could grab out everything that you really don't want and sort of purify back the water in the opposite direction. Any question on osmosis, osmotic pressure? All right. So let's talk a little bit about what is the importance of sort of osmotic pressure and solutions and say the classic example of like our body cells and stuff like that, right? Our cells are really just membranes, and they act as semi-permeable membranes. They allow things in, right? They allow things out of the membranes. So, for example, there are 3 different types of solutions. There's isotonic solution, hypotonic solution, and hypertonic solution. We'll start with isotonic solutions. Isotonic solutions exert the same osmotic pressure as body fluids. That's why most IVs are isotonic. And that is because basically, if we take the classic example of a red blood cell, and if we put it into a isotonic solution, basically the pressure outside of the cell and inside of the cell is basically the same. And what that allows is pretty much nice, even sort of flowing in and flowing out of the cell of like solutions or water, if you want to think about it that way. And that's really good because obviously if you're getting an IV, you're probably in some bad shape maybe, or not so great a shape, or need some help. And clearly they don't want to give you anything that's going to give you even more trouble, obviously, and mess up your cells. So what is considered an isotonic solution? Usually it is 0.9% mass to volume sodium chloride, or sometimes referred to as a saline solution. It can really be any ionic compound, but sodium chloride is very common. And a 5% glucose. Solution. Those are considered isotonic solutions, which means if you put like a red blood cell into either of those solutions, you're going to be in okay shape. You won't have any trouble with your cells. Everything should kind of flow in and out nice and even rate, and no cells or anything will be damaged. So what happens if something else happens, or you put it into a different type of solution? So let's talk about hypotonic solution. Hypo means lower than. That means that the osmotic pressure outside, for example, of the cell is lower than inside the cell. So what's going to happen in this case is we take our red blood cell and we put it into a hypotonic solution. Outside the cell is lower than inside the cell. So osmosis, as we just talked about, means that it wants to go from lower concentration to higher concentration. So what's going to happen is the cell is going to basically let everybody rush in, all the solution. It's going to rush into the cell because the cell is more concentrated than the solution on the outside of the cell. That's not so great for the cell, as it will start to swell and possibly burst, which is known as hemolysis, and that would not be so good. So if you have any solution that is less than 0.9% sodium chloride or less than 5% glucose, that is hypotonic, and you're going to have everybody rushing into the cell. The cell is going to swell and probably burst. Another type of solution is a hypertonic solution. Hypertonic means greater than. So if we take our red blood cell and we put it into a hypertonic solution, what that means is outside of the cell is actually more concentrated than inside the cell. So once again, osmosis here is going to come into play. Your cell is going to go, oh no, everything around me is way too concentrated. So it's going to decide to help out, and it's going to help out by pretty much letting all of its solution out of the cell to try to dilute the outside water or whatever solution that's in. Not really water, but the solution that's in. The result of that is the cell is pretty much going to release all of its fluids, and that's going to cause the cell to start to shrink and go through what's known as crenation. Also, I'm thinking not so great either, probably, in that situation. So ideally, isotonic is really good. We got the equal osmotic pressure. And again, when we really have a difference in the osmotic pressure, say on outside, inside of the cell, that osmosis is going to kick into play, and we're going to get the water to either flow into the cell or out of the cell. Questions out there? So these two numbers are really important to know, as that's your baseline for obviously isotonic solutions, and that's what you want to compare everybody to in terms of that. Any questions on that there? All right, that's what we just talked about. So here again, as you can see, isotonic, regular donut, things flowing in and out all right. We have a hypotonic solution, things flowing in, it pops like a jelly donut all over the place, not so good. Hypertonic, everybody's going to shrink. That's our donut hole, I think, that's left over there in this case. So let's decide what will happen. Will it be okay? Will it swell? Will it shrink? We'll go through crenation, hemolysis. If I take my poor red blood cell here and we put it into the following solutions, if I put it into a 1.5% sodium chloride solution, I put it into a 2% glucose solution, I put it into a 5% glucose solution, I put it into pure water. All right, so for each of these, decide what will happen to the red blood cell here. And those two numbers that we talked about earlier are really important. I'll remember that isotonic solutions, which means everything's going to be good, same osmotic pressure, 0.9% sodium chloride or some type of ionic compound or saline solution, 5% glucose. So when we start out here with 1.5% sodium chloride, it is as simple as 1.5 is a larger number than 0.9. So larger would mean more than, right? So that's going to mean that this is going to be a hypertonic solution, right? That means that we have this situation, whoops, not that situation, this situation right there, where we have on the outside of the cell is going to be more concentrated than inside the cell. So everything from the cell is going to rush out of the cell in an effort to try to dilute it down. And we're going to see it start to shrink, right? And go through crenation, right? And start to be our donut hole happening right about there. Yeah. Any questions on that one there? Taking a look at the next one, which is 2% glucose. So comparing it to our 5%, 2 is less than 5, which means it's going to be hypotonic. So again, in this case, we're going to have actually this situation happening. Outside the cell is going to be less concentrated than inside the cell. That's going to cause everything to rush into the cell through osmosis to try to dilute it down. And we're going to start to see it swell and go through hemolysis there and start to burst, right? How about 5% glucose would be isotonic in that case, right? So nothing bad is going to happen. We're going to get basically this situation here. Everybody's going to flow in and out okay. Lastly, how about pure water? Pure water is not good for your cells. That is hypotonic. Yeah. That is, as we just talked about, pure water has no osmotic pressure, which means it definitely has less of a concentration outside of the cell than inside the cell. So actually what's going to happen is we're going to get it to start to swell in this case and burst again because pure water has basically no osmotic pressure. So sometimes water is not always a good thing in certain situations. Yes. Any questions on hypotonic, isotonic, or hypertonic solutions? Okay. All right, so dialysis is a process that's similar to osmosis. Dialysis allows small solute molecules and ions, as well as water ones, to pass through, but again, sort of traps larger particles. It's pretty much what you're going to do probably this week in lab is this right here. You'll fill a dialysis bag with a bunch of stuff, and every 30 minutes or so that you go and check the solution on the outside and see what has come out of the bag and eventually you will pop the bag and see what's still left in the bag, if I am not mistaken. So a dialysis bag here again allows the smaller molecules basically to move in and out. It has small holes. You can't really see them with your naked eye, but again, it has small size holes that allow certain size particles to move in and out, while obviously trapping those larger particles as well. In our body, right, we have certain functions that do dialysis for us, right, and kind of get rid of some stuff that we do not want in our body as waste products, and obviously keep things that we will need through our kidneys. Any questions on that there? Okay, so okay, so we're going to go back into the notes there, right around where it says mass percent, and that's where we're going to pick up. So we're going to talk now about some concentration units for solutions. And there's a bunch of different sort of concentration units we're going to talk about. We can talk about some percent concentration units. Then we'll talk about molarity, which is, again, kind of the major unit that's usually used for solutions. So let's take a look at the first one. So the first type of concentration unit for solutions is referred to as mass percent, is sometimes referred to as mass percent, and sometimes abbreviated M/M percent, or mass to mass percent. Some people use W over W, weight over weight, but M over M and W over W is basically the same thing. Now, the mass percent is the mass of the solute over the mass of the solution times 100%. The important part of this calculation is actually the bottom. Remember, as we talked about, that the solution is really made up of two things, and it's made up of the solute and the solvent. So you want to make sure that when you get to a problem where you're calculating the mass percent, that you actually do get the mass of the actual solution and not just the solvent, which is a very common thing that people will do. And it's really common because in these type of problems, they oftentimes will give you that information separate from each other. So they'll kind of give you the mass of the solute, they'll give you the mass of the solvent. And again, people just go, oh, well, that looks like the larger number, so I'll just take that one. And they're just getting the solvent. If you had a solution, for example, that was 4.5% by mass sodium chloride, you could kind of convert that into a usable sort of conversion factor. And usually when we're dealing with percentages and we want to kind of turn it into a number, basically we assume 100 of it, and that makes the percentage and the numbers basically the same. So if in this case, what that would mean is you would have 4.5 grams of sodium chloride in 100 grams of solution. And you can use it as a conversion factor like that. You also could flip it around and go in 100 grams of solution. There would be, in this example, 4.5 grams of sodium chloride. So sometimes it's easier in these type of problems to work them more as a dimensional analysis type of problem rather than a plug and chug, but you could just plug and chug into here as well and solve for whatever you may be looking for. But doing a conversion route might be helpful as well. So if you are going to have the percentage, basically just assume you have 100 and it does turn it into there. So let's take a look at one here and see. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of this solution. So take a minute or two, calculate the percent by mass here. Okay, so let's take a look. So we're looking for the percent by mass here, and that's going to be our mass of our solute divided by the mass of the solution times 100%. So in this case, our solute is the calcium chloride. That's going to be our solute. That is the smaller part. In this case here, our water is our solvent in this case. So that means that the mass of our solute will be 2.50 grams. That also means the mass of our solution should be our solute plus our solvent. So in this case, it should be 2.5 plus our 50, giving us 52.5 grams as the correct mass of our solution. Again, not just 50, otherwise that's just the solvent, that is not the actual solution. And again, very commonly they're given separate to each other here. So now we got everything we need, we could plug it in, and we're gonna end up with 2.5 divided by 52.5 times 100%. And we will end up here, I think, 4.76% by mass. And you could use something like calcium chloride in this case. Any questions on that calculation? So again, very common error people make to just grab the solvent and not adding them together in this case. Any questions? Okay, let's take a look then at another one if there's no questions. Concentrated hydrochloric acid contains 37.2% by mass hydrogen chloride. What mass of hydrochloric acid is contained, or hydrogen chloride is contained in 35.5 grams here? So in this case, we are given the percent mass to mass of 37.2%. We also have the mass of the solution given to us, which is 35.5 grams. So you definitely have this. You have this. You can solve for the mass of the solute by plugging into there. You could also do more of a dimensional analysis calculation here. It comes out the same. So for example, if we wanted to take that 37.2% in this case, that means that there are 37.2 grams of hydrochloric acid and 100 grams of solution. Or you could use it in the opposite way. 100 grams of solution will have 37.2 grams of HCl. So if we take a more dimensional analysis approach here, we have 35.5 grams of solution. We want to go opposites to cancel, which means we actually do want to use one here on the left. That will give me 37.2 grams of HCl and 100 grams of the solution. Grams of solution will cancel, and that will tell me how many grams of HCl I got going on there. 35.5 times 37.2 divided by 100. Gonna give me about 13.2 grams of HCl. That is basically the exact same calculation as if you just plugged and chugged it into the equation. And if you just put it into the equation, you would have 37.2% equals the mass of the solute divided by our 35.5 grams times 100%. We would multiply the 35.5 to the other side and divide by 100%. And again, that will cancel out both of those. So it's basically the exact same one. You should get the exact same answer. So if you want to plug it into the equation, you can. If you want to take more of just a dimensional analysis, get rid of the units type approach, you could do that as well. Any questions on that there? And obviously, the percentages here cancel out, and we end up with grams at that point. Yeah. Question on mass percent. Really, the one you got to watch out for is that bottom part of it. There are a couple of other type of percent concentration units that kind of go with percent mass to mass. They're kind of similar. So let's take a look at a couple of those as well. The next sort of percent unit is what is referred to as volume percent. And that is the percent volume to volume, like percent volume alcohol and all that kind of stuff. That is the volume of the solute divided by the volume of the solution times 100%. This one you usually don't have to worry too much about because usually they'll just probably give you the volume of the solution rather than the other one where they kind of separate the solvent and the solute up. It works the same way. So if you had a same example there, 4.5% volume to volume percent of, say, sodium chloride, what that would mean is you have basically 4.5 milliliters of sodium chloride in 100 milliliters of solution. And again, you can use it just like a conversion factor and flip it around the other way, that you have 100 milliliters of solution and 4.5 milliliters of sodium chloride. So once again, a lot of times this is, in most cases, milliliters and milliliters, which is common. Volume is typically what we got going on there. Another percent concentration that works similar is percent mass to volume, or weight to volume is sometimes referred to. And that is the grams of the solute over milliliters of solution times 100%. Once again, sometimes people call this W over V for weight to volume. But it is the grams of solute over milliliters. That's basically like grams per milliliters. It's kind of like density. Yeah, so it's kind of the same idea there as what we saw before. Works the same way as everybody else. If you have the 4.5% mass to volume sodium chloride, that would mean you have 4.5 grams of sodium chloride in 100 milliliters of solution, and vice versa. Again, you could flip it around the other way and use it like that as well. So these obviously you could plug and chug into the equations as well. And again, if you're given a percentage concentration, you could turn it into a usable conversion factor there by assuming 100. Question on that one there. So let's take a look at an example here. Let's see. What is the mass to volume percent of Br2 in a solution prepared by dissolving 12 grams? All right, so here we're dealing with our percent mass to volume. So that is our mass of our solute divided by our volume of solution times 100%. In this case, we have 12 grams of Br2, which is being dissolved. So that is our solute. And in this case, we have 250 milliliters of solution, carbon tetrachloride. And we will go with 12 divided by 250 milliliters times 100%. And that's going to get us 12 divided by 250 times 100%. Maybe not 1,000%. Try that again. Kill alpha 0. There we go. At 4.8% will work. 4.8% mass to volume of our Br2 solution here. Here, the answer again is usually given as a percentage, since we're looking for our mass to volume percent. First off, any questions on the calculation? By the way, in this case, why do we use carbon tetrachloride rather than water with Br2? Br2 is what type of molecule? Is it polar, non-polar? It is two of the same, which means it is non-polar, right? For sure. And that is not going to work great with water, which is polar, right? So that is the crossover. That's not good. But if you quickly just kind of sketch up carbon tetrachloride, looks something like this. And you might remember, I'm not going to put all the dots in, but this is basically one of those symmetrical geometries, which means this is also a non-polar molecule. So that non-polar guy and the Br2, which is non-polar, are going to work perfectly fine together, as they both are using the same type of intermolecular forces to basically interact with one another. So again, as we mentioned the other day as well, Water is really great for polar and ionic things, but it's not really great for nonpolar things. So it's not always the best choice in terms of a solvent. Question on that there. Let's try one more here. Calculate the grams of KCl and the grams of water in 225 grams. Okay, so let's take a look and see. So obviously we're dealing with percent mass to mass. So we're given, we're looking for the mass of the solute here. We do have the mass of the solution, which in this case is 225 grams. And we have the percent by mass there of 8%. I know that I'm looking for the mass of the solute because I'm asked for the grams of KCl. This is a KCl solution. As I mentioned before, the name of the solution is the solute. So if you're looking for KCl and the solution is a KCl solution, then you're looking for the mass of the solute. That's how I know that the other guy was basically the solution, even though I think it says solution, but just in case. That's how you can figure that out. So again, you could plug and chug into the percent mass to mass equation. You could also take more of a dimensional analysis approach. So that's what I'm going to do in this particular one. I'm going to take my 8%. And what that means in this example is that there are 8 grams of KCl in 100 grams of solution. Or again, you could flip it around the other way if you needed to. 100 grams of solution, there would be 8 grams of KCl. So that's basically what my 8% means in this case. So since I do have the mass of the solution here, which is 225 grams of solution, I want the solution to cancel. So I'm going to use the one on the left here, which will do that for me. That will also leave me the grams of KCl, which I'm looking for. And again, this is really the same math you would be doing if you plugged it into the formula and just solved for the mass of the solute. We'll take 225, we'll times it by 8 and divide it by 100. You're basically taking 8% of that, and that's going to give you 18 grams of KCl. I lost my 1 on my box there. There we go. Put it back in. Any question on that so far? So that is the mass of the KCl. And we're also looking for how many grams of water, which is our solvent in this case. So once again, that is our solute. And that means in this case, this is our solvent. And in this particular case, water is a good solvent because that's an ionic compound. So that's going to work really well with the polar water. Remember that basically the mass of the solution, as we talked about, is the mass of the solute plus the mass of the solvent. So we do have the mass of the solution. We just figured out the mass of our solute in this case. So we can basically subtract to get the mass of the solvent, which is our water. Mass of the solvent will be the mass of the solution minus the mass of the solute. So that's going to give me 225 grams minus 18 grams. Going to get us 225 minus 18, looks like. About 207 grams of water we need to toss in there, along with our 18 grams of KCl, and we will have a solution that is basically 8% KCl. Any question on any part about there? Question on percent concentration. So I would say not used tremendously a lot, percent mass to mass and, volume to volume. They do pop up, but you obviously need to know how to calculate those. Any questions? All right, then let's talk about really the concentration units that we use really the most with solutions, and that is molarity. And molarity is the most common sort of unit of concentration that we use. So the molarity is basically for capital M, and it really is moles of solute over liters of solution. Most people just think of it as moles over liters. You could think of it as a formula, kind of like density, moles over liters. If I wanted liters, that would be moles divided by molarity. And if I wanted moles, that would be liters times molarity. So kind of like density, this one as well, we do solve for any of those three things depending on the situation. So we you should know how to properly rearrange it. And again, you may be asked to solve for any of those guys that are there. So another type of units that we won't probably use too much here is milliliters. Molarity is millimoles over milliliters, and that gets you back to molarity. If you get rid of the milli part of it, gets you moles per liter, which is molarity. A couple important things when you do have the molarity given to you. If you had something that was a 4.5 molar sodium chloride solution, I would highly recommend when you do calculations that you get rid of the big M and not just leave it as big M. And that is because most people, when they do leave it as big M, which is the molarity, have no idea where like liters is or the volume is. They forget all about the volume part of it and they just think moles because it says M. So I would highly recommend when you're doing calculations that you convert that into 4.50 moles over a liter. The number should stay with the moles part. You should use it. The liters on the bottom should be 1. Now you could clearly see both units and you hopefully won't forget about the lonely liters. It gets forget about a lot when people do this. So highly recommend getting rid of the big M when you're doing calculations so that you can see that. Also really important is if you are using molarity by itself like we are here, the volume does need to be in liters to properly cancel out. Otherwise, if you multiply milliliters times molarity, you do not get moles. You actually get, as the bottom says there, you get millimoles, which is different. It's off by a factor of 1,000. So make sure always that the volume gets converted to liters when you're using it with molarity and you're just doing the molarity sort of formula. Other important things is very common to get to moles. That is a lot of times a grams to moles situation. And molar mass is used a lot to convert things from grams to moles like we did in the previous chapter. So that also is very common. So grams to moles, very common with molarity. Also the conversion that hopefully you know, but you will use a lot is 1 liter is 1,000 milliliters. Also a conversion factor that's used a lot to convert our volume from milliliters to liters. That is because usually milliliters is a very common unit, obviously, of volume. So that conversion is used a lot. So when we do have something that is written as 1 molar sodium chloride, and that is how we refer to it as 1 molar, it's basically 1 mole of the solute per liter solutions. How concentration works between an ionic compound and its ions is it works kind of like stoichiometry. So for example, when we have something that is 1 molar sodium chloride, when sodium chloride's in solution, as we've talked about, it is a strong electrolyte, which means it's going to break apart into sodium ions and chloride ions. How concentration works if you're not interested in the whole thing, but you're just interested in maybe one of the ions, is you need to get the concentration of the ion by itself sometimes. So if this thing is basically 1 molar, this is a 1-to-1 relationship between the sodium ion and the whole thing, which means the concentration of this guy will also be 1 molar. You basically take 1 times 1 and you get 1 still. When we look at the chloride, it's a 1-to-1 relationship between the whole thing and just the chloride ions. It is going to be 1 molar. Now, let's say I had a 1 molar solution of calcium chloride. When calcium chloride breaks apart in solution, it is going to break apart into its ions. We will have a calcium ion, and we will have 2 chloride ions. Now, when we look at the concentration here between calcium chloride and the calcium ion, it is a 1-to-1 relationship. which means you could take 1 times 1, which will give you 1 molar. So we got 1 molar of calcium ions floating around in that solution. But when I look at the calcium chloride to the chloride ions, it is a 1 to 2 relationship. So how you adjust the concentration for the chloride ions is you take 2 times the 1 molar, because there's 2 of them, and that gives you 2 molar calcium chloride. So in that solution, when that guy goes for a swim, you basically have twice the concentration of chloride as you do calcium. That makes sense, right? You get a 2 for 1 deal, right? So you got twice as much chlorine floating around as you do calcium. It's not additive, so clearly 2 and 1 doesn't equal 1, right? When you add those ions back together, but that's how concentration works. To show you really how we get there, that is the short version. You basically times it by 2. The long version of that calculation is if I had 1 molar calcium chloride, that would basically be 1 mole of calcium chloride per liter of solution. And I would do basically stoichiometry here. It is a 1 to 1 relationship between the calcium. So 1 mole of the whole thing gives me 1 mole of the calcium ion. Those guys cancel, gives me 1 mole of calcium ion per liter, which is 1 molar of the calcium ion. When I do the same calculation for my chloride, it is again a 1 to 2 relationship. So for 1 mole of the whole thing, I get 2 moles of the calcium ion. Moles cancel, gives me 2 moles of calcium per liter. Not calcium, but chloride. Sorry. Chloride. There we go. Which would give me 2 molar of the chloride ion. So that's the long version. Quick version is multiplied by the coefficient when it breaks apart. So it breaks apart into 3 ions. Take the concentration, multiply it by 3. So that's sort of the quick way that you could get the concentration of just the ion rather than the whole thing together. And there are certain problems where they're looking for just, what the individual ion is, not the entire ionic compound as it's floating around in there. Question on that relationship. Okay. All right, so why don't we try one here to finish? Calculate the molarity of a solution prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters. Potassium, I think, is 3910. Bromine is, we'll go with 70. Okay, let's take a look here. So again, in the end, we're looking for molarity, which is, again, moles per liter. So when we look at our problem, do we have any of that given to us? We do have the volume, and it is in liters, so it's good to go. We don't have to really do anything to that. We are looking for the molarity here. So that means the other piece of information we have is grams, and that is not moles, but we can use, again, the periodic table to convert our grams into moles. So we will need the molar mass of KBr, which is just adding those together, I think. And that's going to give us 119 grams per mole. So we're going to convert our grams of our solute here, which is our KBr, into moles using the molar mass from the periodic table. The grams will go on the bottom so that they cancel. And that's going to give us like a 0.131 moles of KBr. At that point, we now have the top number. We have the bottom number that was given to us. All that's left is to plug it in. So we're going to get 0.131 moles over 1.25 liters. And if we do all that good stuff there, we're going to end up with here, call it 0.105. The units are moles per liter as they do not cancel out. KBr, R, you can write it at the end as 0.105 big M KBr. So either one here would work. Question on that calculation. So that's a very common thing, grams to moles. Also, like I said before, very common milliliters to liters conversion in there as well. It's a very common thing that she has to do. It has to be liters and it's got to be moles when you're calculating the molarity. Any questions on that?